Okay, so we'll start with question 1 on finding the derivatives of inverse functions. Okay, so like we did in class, we're going to take the inverse function equation, convert it into an implicit equation, and then solve for y prime. Okay, so question 1.1, y is equal to tan inverse x. Okay, so we know it's an inverse function because it's to the power minus 1. That is not an exponent. Okay, that is to show it's an inverse function. I think over 10 students were writing it as 1 over tan x. That is wrong. Okay, if we have tan minus 1, it means inverse tangent, not reciprocal of tangent. Please do not do that. And the same goes for cos, sine, and any other trig function. That minus 1 does not mean reciprocal, it means inverse. Okay, we could also write this as arctan. So arctan means the same thing as inverse tan. Okay, so maybe if you see tan to the minus 1, write it out as arctan, and then you won't get confused with those powers. Okay, so please do not write 1 over the trig function. Okay, so what we do, since it's an inverse, we take the tangents on both sides. So tangent y is equal to tangent of arctan, or inverse tan of x. They cancel. So we're left with tangent of y is equal to x. Okay, everybody should be writing this down. So now we have an implicit equation. We see that the y is inside some other function. Okay, that's what we mean by implicit. So what we do, we want y prime. Y is inside another function, so we need to differentiate both sides. So we do that. D by dx of tan y is d by dx of x. Okay, we just take the derivative of both sides. That is the standard procedure for implicit equations. Okay, now the derivative of tan, that's going to be sec squared. Good. But like I said, y was inside another function. Whenever you see that or hear that, we know to use the chain rule. So we need to differentiate the inside function, which in this case is y, so it's going to be y prime. The derivative of x, that's just 1. Okay, I see a lot of students got up to this point, which is good, but then you messed up with the trig functions there. Okay, so when we take this over, it will be 1 over sec squared y, and a lot of students left it at this point. Okay, so you didn't get all the marks. What we want is a function of x, not y. So if we have sec squared y, we need to rewrite it in terms of x. Okay, so this is only halfway. We need to complete it. So to do that, we look at how x is defined. Right? X is equal to tan y. Since we know x is equal to tan y, we can rewrite sec squared y in terms of that. So sec squared y, that's 1 plus tan squared. Why am I doing that? Well, because tan squared y is just x squared. Okay, use your trig identities, use what's given to rewrite it in terms of x. So this will be 1 over 1 plus tan squared y. Again, why am I using that identity? Because if we go up a bit, we see that tan y is x. That's why I'm using that identity. We need to incorporate tan. Okay, and tan squared y, that's going to be x squared. So it's 1 over 1 plus x squared. If you ever forget that identity, you start off with the one that you do know. So that's sine squared, let's just put it as t plus cos squared t is 1. Okay, we want to get tan into this. So we've got sine. How do we get from that to tan? We can divide through by cosine squared. So sine squared t over cosine squared t plus cosine squared t over cosine squared t is 1 over cosine squared t. Okay, so again, if you forget the identity, you can rederive it on the side. Okay, you can get part marks for that. You've shown some work. Okay, so sine squared over cos squared, that's going to be tan squared, which is what we want. Cos squared over cos squared, that's just 1. 1 over cos squared, that's sec squared. Sorry, sec squared t. Okay, so if you forget, just rederive it on the side. If you get the final answer wrong, you can still get part marks for that working. But if you just leave it and don't try to figure out what the identity is, I can't give you anything. Okay, so if you do forget something, try to figure it out on the side. You're guaranteed some part marks for trying. Okay, and we've got our answer. Okay, 1 over 1 plus x squared. Okay, please do not leave your answer in terms of y. We are looking for a function of x. Okay, so you have to convert it back. Okay, let's have a look at the next one, number 2. Okay, we have y is equal to cos inverse of 2x. Again, that does not mean reciprocal. You could write it as arc cos 2x. Okay, so if you think you're going to get confused about that minus 1, rewrite it as arc cos or inverse cos, and you won't get confused. Okay, again, please do not write it as a reciprocal. Okay, so same thing as before. We've got an inverse function. We take cos on both sides, and that will get rid of that inverse. So we're going to have cos y is cos of cos inverse of 2x. The cos and the cos inverse, they cancel, so we're just left with the 2x. Cos y is equal to 2x. Okay, very similar to what we had before. Now we take the derivative on both sides. Why do we take the derivative on both sides? Because we have an implicit equation with y. See, y is an inside function there. To find y prime, we take the derivative on both sides. So d by dx cos y equals d by dx of 2x. Okay, I also saw a lot of students just didn't write down the 2x. So you started off with y equals cos inverse 2x, and on the next line, it was just cos inverse x. Okay, so it wasn't just one student, it was quite a few. Please make sure you read the question carefully, and if you're going from one line to another line, make sure you're not leaving anything out. So if you have cos inverse 2x on line 1, check that you have that on line 2. Okay, a lot of things were disappearing from one line to another line. Okay, now we take the derivative, outside function first, that's minus sine y. Inside function is y, so that's going to be y prime. The derivative of 2x, that's just 2. Okay, y prime is minus 2 over sine y. Again, a lot of students got up to this point, which is good, but this is only halfway. What we need to do is change it from being y to something with x, like we did before. And how do we do that? Well, we look at what we've got. We've got cos y is equal to 2x. Here we have sine y. We want to write it as cos y. We have it as sine y. We know the relationship between the two. We can use that. So put the working on the side. We know cos squared y plus sine squared y is 1. Doesn't matter what y is, that's always true. Here we've got sine y, so let's solve for that. So sine squared y is 1 minus cos squared y. But cos y is 2x, we know that, that's from our previous working. So we can replace that. Sine squared y is 1 minus 2x squared. Now that squared is on both the 2 and the x. It is 2x, all of it squared. Again, many students were writing it as 2x squared, where the squared was just on the x. Okay, if you have something in brackets to an exponent, it goes on both the terms. So this is sine squared y is 1 minus 4x squared. Okay, the squared goes on both of them. I think about 5 or so students were not doing that. Okay, again, we're looking for sine y. We've got sine squared, so we just take the root. We get root 1 minus 4x squared. Okay, we can substitute that. So y prime is minus 2 over the square root 1 minus 4x squared. Okay, a few students did get this fully correct, which was good. And then a lot of students just stopped on that previous line and didn't write it in terms of x. Okay, so please make sure you answer the question fully. There were, I think, 2 or 3 students that just wrote down the answer. So these derivative of trig functions, those are pretty known. So like the derivative of sine inverse, the derivative of tan inverse, they are commonly known. Some students were just writing down the answer. Okay, so if you see the question is out of 4, you can't put one line down. Okay, I'm not going to put 4 ticks for one thing written. Okay, so if you see the question is out of 4, show all you're working. If the question is out of 1, then you can just put the answer down. I'm not looking for all the working. Okay, so please use that mark allocation as a guide to see how much you actually need to do. Okay, if it's 1 mark, just put the answer. If it's 4 marks, I'm looking for a bit more than that. Okay, question 3, let's have a look at that one. So here, y is equal to x sine inverse x. Okay, so this one's a bit more tricky than the ones before because we have x times sine inverse. Now, x times sine inverse, that's not an inverse function. Sine inverse by itself, that is an inverse function. So we can't just take sine on both sides. It's not going to cancel, right? Sine is not the inverse of x sine inverse. Okay, so we can't just take sine on both sides. So instead, we're going to take the derivative on both sides because we're going to try to find y directly. Okay, so let's put a comment here, don't, and then we'll put here sine of y is sine of x, sine inverse x. That x causes a problem. Okay, so don't write it like that. Instead, we're going to take the derivative on both sides. Okay, I hope everyone's writing this down. So, d by dx of y is d by dx, and I'll put this in brackets because it's a product of 2 things, x sine inverse x. Okay, so now d by dx of y, that's just y prime directly. We don't need to worry about any chain rule or anything like that. So y prime. Okay, now we use the product rule. We've got a product of 2 functions. Just because the second one is an inverse function doesn't mean we don't use the product rule. We use it as is. So we differentiate the first term, so that's 1. We leave the second alone. Plus, we leave the first one alone, we differentiate the second. Okay, we can put that in brackets there. Okay, so I'm going to leave that as a bit of revision, calculating the derivative of sine inverse. Very similar to what we did with cos and tan. Same sort of working. Okay, so we'll end up with 1 over the square root 1 minus x squared. It's very similar to what we had with cos. So here, y prime will be sine inverse x plus x over square root 1 minus x squared. That working you can do on the side. Okay, again, very similar to what we had with cos. So here, this working here, so we had the sine at the bottom, and then we did this working on the side, very similar to this case here. Okay, so I'll just put a little asterisk there that you'll do on the side. Okay, so that was question 1. Okay, let's have a look at question 2. Okay, so question 2, that was on evaluating limits. Now, question 2 is not labeled L'Hopital's rule, so you can't just use L'Hopital's rule whenever you see a limit. So if you can use L'Hopital's rule, and we went through those cases, then you use it. So that is if it's of the form 0 over 0 or infinity over infinity. You don't just apply it whenever you see a limit. It's only certain cases. Okay, I see people were using L'Hopital's rule for every single one and just ignoring those cases. Please make sure that your function is of the form, with that indeterminate form of 0 over 0 or infinity over infinity. If it's not of that form, you cannot use L'Hopital's rule. Okay, so let's look at this one. We have the limit x goes to minus infinity of x squared e to the x. Okay, this, we cannot use L'Hopital's rule with this, because if x goes to negative infinity, the first part goes to infinity, the second part goes to 0, so this is 0 times infinity. It's an indeterminate form, that's correct, but it's not the one that we need for L'Hopital's rule. L'Hopital's rule needs infinity over infinity, or 0 over 0. Okay, so just because it's an indeterminate form, again, you can't just use L'Hopital's rule directly. It has to be of this form. Okay, now some students did identify that they need L'Hopital's rule, but they just differentiated the function. They didn't change it at all, it just differentiated x squared e to the x. That's wrong. Okay, we need it to be of the form infinity over infinity, or 0 over 0, and then you differentiate the top and the bottom. Okay, please do not just differentiate the function right away. Okay, so what do? We need to rewrite it in one of those forms. So this will be the limit as x goes to minus infinity, x squared over e to the minus x. Okay, so why did I do it this way? If I wrote it the other way, which a lot of students were doing, as e to the x over 1 over x squared, that's right, that is an indeterminate form. We can use L'Hopital's rule, but look at the top, e to the x. If we differentiate that, we get e to the x again. If we differentiate it again, we get e to the x. It doesn't change. So if we use L'Hopital's rule, we're going to be going around in circles because the numerator doesn't get any simpler. It just stays like that forever. So that may be of the form 0 over 0 or infinity over infinity. You can use L'Hopital's rule, but this form is not going to help us. Okay, using L'Hopital's rule with this, we're going to get back where we started. So that doesn't work. So test it. Do a line of L'Hopital's rule. If it doesn't get any simpler, then maybe you've written it in the wrong form. Okay, and then you try again with a different form. Okay, so please check. When you're using L'Hopital's rule and you're writing it in this indeterminate form, check. If I differentiate the top and the bottom, does it get simpler? Does it stay the same? Or does it get even more complicated? That will allow you to test if you've done it in the correct form. Here, we've got x squared at the top. If we differentiate, we get 2x. If we differentiate again, we get 2. It's getting simpler. So that must mean it's the correct way. This e to the x at the top doesn't get simpler. We've done something wrong. So please make a note on that. Check to see, is this form actually right to get simpler? Okay, so here we use L'Hopital's rule. We differentiate the top and the bottom. So that's the limit as x goes to minus infinity. We differentiate the top, that's 2x. Okay, it's simpler, so that's good. And then we have minus e to the minus x. Now again, we're going to get indeterminate form there. So we can do it again. Okay, you do it again, the top simplifies, take the limit, we get 0. Okay. For these ones, you don't need to show the derivative on the top, derivative at the bottom. If you can do that in your head, that's perfectly fine. If you want to write out every single step, that's fine as well. Okay. Okay, but as long as I can see how you got from one line to another, I'm happy with that. Okay, so that was the first one. Let's have a look at the second one. So this was limits as x goes to infinity, 1 minus 1 over x to the 2x. Okay, so this was done in class. This was one of the questions we went through together. Okay, so we've got a function as the base and we've got a function as the exponent. So we did this in the Monday lecture. Whenever you have a function as the base and a function as the exponent, you take the logarithm on both sides. So we can call this L for limit. You can call it whatever you want, but L is fine. So we have the natural log of L is the natural log of the limit as x goes to infinity, 1 minus 1 over x to the 2x. Okay, a lot of students were just differentiating right away without doing any work. Okay, please do not do that. Okay, so the natural log and the limit, we can swap those around, okay, because the logarithm is continuous. So we have the natural log of L equals the limit as x goes to infinity. Okay, if we take the logarithm, the exponent comes down, that's just the log rule. So it will be 2x, the natural log, 1 minus 1 over x. Okay, so I did 2 steps in one. We swap the limit and the log because the log is continuous, and we take the exponent down using the log laws. Okay, if you don't remember your log laws, please go back and look at them. Okay, it's very important that you know your log laws. Okay, so what type of indeterminate form do we have here? If x goes to infinity, the first part goes to infinity, the 2x. What about the second part? 1 over x will go to 0. The natural log of 1 is 0. So it's an infinity times 0 situation. So infinity for the first part, the second part ends up being 0. So it's that type of indeterminate form. Okay, so what do we want to do? We want to rewrite this in the form infinity over infinity or 0 over 0. Now we need to choose what's going to be the numerator, what's going to be the denominator. Okay, so I'll just write down which one needs to be which, and then we'll see why that's correct. So we have the limit as x goes to infinity. We can take the 2 out, that doesn't affect anything. So we're going to have the natural log 1 minus 1 over x divided by 1 over x. So the x that we had in the numerator previously, we're going to write as 1 over x in the denominator. Okay, so a lot of students did get to this point, which is good to see, but then the derivative went wrong. Okay, so let's see. Why did I put the natural log in the numerator? Well, when I differentiate the natural log, I'm going to have 1 over that term, and then we do the chain rule. We'll see that this term inside here, when we use the chain rule, cancels with this denominator. So whenever you have a 1 over x, when you differentiate it, you get 1 over x minus 1 over x squared. Here we've got a 1 over x in the denominator. So we can see that further down the line, we're going to get cancellation. You could do it the other way around. You'll get the same answer, but it's just a bit more work. Okay, so maybe try it out swapping the numerator and denominator, and then see what you get. Okay, it will be a bit more work, but manageable. Okay, so now we take the derivative of the top and of the bottom. So the natural log of L is 2, limit x goes to infinity. We differentiate the top. The derivative of the logarithm is 1 over the inside stuff. So that will be 1 over 1 minus 1 over x. Chain rule, we differentiate the inside part. So the derivative of 1 over x, that's minus 1 over x squared. But we've got another minus there, so it will be plus 1 over x squared. Okay, that's for the top. What about the bottom? Differentiating 1 over x, that's minus 1 over x squared. Okay, see what I mean by the cancellation. So you pick the top and you pick the bottom such that things will cancel nicely. Okay, if you don't see it at first, you can try one way and then try swap them and try the other way. You'll see which is better. Okay, but here the top and the bottom will cancel. There and there. Remember the minus sign. So we have the natural log of L is 2 times the limit as x goes to infinity, 1 over 1 minus 1 over x. Okay. Also, another thing that I noticed, when writing fractions over fractions, a lot of students got confused with the cancellation. Okay, please don't try to fit everything onto one line. If you need to write the top over 2 lines and the bottom part over 2 lines, just to give yourself some space, please do that. Okay, I see a lot of students are trying to fit this all on one line, and then you get mixed up with what goes where. Okay, so a fraction divided by another fraction, give yourself space to work with that. If you try or write it in one go, you're gonna mess up. Okay, but here we can clearly see this term in the numerator, big line, we know what that means. The same term in the denominator, clearly they cancel. Okay, so give yourself space to work. Now, if x goes to infinity, the 1 over x part, that goes to 0. Yes? Negative, over there. Yeah, so the negative from the denominator, you can just write that at the top. Okay, or you can write it outside. So since it's a constant, we could put it there. Okay, so sometimes the minus signs are a bit difficult to work with. You might lose track of them. So any constant you can take out. Okay, that might make things a bit easier to work with. Okay, so this minus sign, you can take it right out to the front, and then you don't have to worry about it. Okay, the 1 over x, when x goes to infinity, that part's going to go to 0. So we're left with 1 over 1, which is just 1. We don't need to worry about that. So the natural log of L is minus 2. Okay, a couple of students did get to this step, which was great. However, I'm not looking for the natural log of L, I'm looking for L. So you forgot the very last step, exponentiate both sides, and we get e to the minus 2. Okay, so please, when you get to this very last step of the natural log of L equals something, make sure you solve for L. I'm not interested in what the natural log of L is. I want L by itself. Okay, last one for question 2. This was the limit as x goes to 0, x cubed 1 minus cos 1 over x. Okay, so we did something similar to this in class, and it was one of the tutorial questions. Okay, so let's just see what happens when x goes to 0. The x cubed, that's going to go to 0. Okay, so the first part 0. What about the cosine? If x goes to 0, 1 over 0 goes to infinity. Okay, in the previous assessment, a lot of students were writing that as the sine, it was sine 1 over x goes to infinity. That's wrong. Cos of 1 over x is always bounded by minus 1 and 1. Okay, so I did go through that previously when we looked at the sine function. So we have minus 1 is less than or equal to cos 1 over x less than or equal to 1. Okay, so please no talking. So previously we looked at the sine function. We said that was bounded. Doesn't matter what the inside part is. Sine of 2, that's between minus 1 and 1. Sine of 1,000,000, that's between minus 1 and 1. Doesn't matter what the inside is. Even if it's 1 over x or 1 over x squared or the natural log of x, makes no difference. The cos function and the sine function is always bounded. Okay. So we use that as our first step. So minus 1 is less than or equal to cos 1 over x, which is less than or equal to 1. Doesn't matter what x is, you can ignore it. Now, what are we looking for? We have that inside part, which is cos, but in the question we've got minus cos. So we need minus cos here. So let's multiply through by minus 1. So we're going to have 1 is greater than or equal to minus cos 1 over x, greater than or equal to minus 1. Whenever you multiply or divide by a negative, the inequality signs flip. Okay. Okay, I hope everyone's writing that down. Okay, now we don't have minus cos, we've got 1 minus cos. So we need to add 1 to everything. So we're going to, please no talking while I'm working. Okay, so we add 1, we have 2, and then 1 minus cos 1 over x greater than or equal to 0. Okay, but we're getting closer. We've got 1 minus cos of 1 over x, but the question has an x cubed. So we multiply through by x cubed now. And then we can swap this around to write it in the proper way. So we have 0 less than or equal to x cubed. 1 minus cos 1 over x is less than or equal to 2x cubed. Okay, so I just multiplied through by that. Okay, a lot of students were writing this statement like this. Okay, so they just put all those terms and then put the bounds. That's wrong. Okay, you start off with the single trig function by itself. So whether it's cos or sine, we start off with that. We know the bounds, and we work up to the question slowly. So we start off with the cos, and then we need minus cos. So we multiply through by minus 1. Then we add 1. Then we multiply through by x cubed. Don't just write down the final function and say it's between minus 1 and 1. Okay, that's wrong. Start from the very simple part and work up to what you need. So this is wrong. Okay, now we've got something like this, where the left-hand side is 0. If we look at the right side, 2x cubed, if x goes to 0, that goes to 0, no issues. The left and right limits are 0, which means the middle limit is also 0. So we have the limit, x goes to 0, x cubed, 1 minus cos 1 over x must be 0, right? Because both left-hand limits and right-hand limits are 0. Okay, so important takeaways for this one. So first thing, please identify when you can use L'Hopital's rule and when you can't use L'Hopital's rule. Here, we can't use L'Hopital's rule. Right? It's not an indeterminate form. It's not 0 times infinity. It's not infinity over infinity. It's none of that. So when evaluating this limit, you need to use something else. Okay, in this case, we used the squeeze theorem. If you can think of another method, that's fine as well. Right? This is just my solution here. Okay, now if you are going to use the squeeze theorem, start off with the simplest part of your function. That's this bit. That's the simplest part, because you start with that, we know how to bound it. Then, once you've written the bounds for that, you can build up to what you need. Don't just write down the full function and say it's between minus 1 and 1. No. We start off simple, and with each step we build up to where we need to go. Okay. And then once you've got the full function in the middle, then you can do your limits on either side. Okay, and then you can get your answer. Okay, let's have a look at question 3. Yeah. So, repeat 4. The last part. So here, if we take the limit as x goes to 0, the left side, that's always 0, so we know that's 0. On the right side, if we take x goes to 0, this right-hand side goes to 0. So the left is 0, the right is 0, which means the middle must also be 0. Okay. Any other questions on that? Okay. Question 3. Okay, so we had the following function and we wanted to find an approximation. It was x squared plus x plus 1 over x cubed plus 1. Okay, and this was at the point 0, 1. Okay, a lot of students were taking this as an x value. They were saying x equals 0, 1. Right, that's not a decimal. If I have bracket 0, 1, it's a point. Right, and the question said it was a point. This is a point in the Cartesian plane. This is not 0.1. Right? Because the question said the point 0, 1. You know what a point is? It's some a comma b. Okay. If it is an x value, the question will say x equals 0.1. Okay. And just a note here, this comma, right, that's standard notation. If you have a comma, it means you're separating things like in a coordinate and so on. if you're writing a decimal, it's always a dot. Okay, so if you do see that in the notes and so on, that's the distinguishing feature between the two. So a point, a Cartesian point, like you've seen in analytical geometry and so on, bracket A, comma B, close bracket. That's a x, y value pair. 0.1, that's the decimal form of 1 over 10. Okay, please don't mix that up. So again, the question said point 0.1, that is x value. So I'll say if it's a value or if it's a point. Okay, so we need to find the derivative to get the gradient. Once we have the gradient, we can find the tangent line. So we need f prime. Okay, so a lot of students were ignoring the quotient rule and just wrote d by d, please don't write this down, d by dx of the top divided by d by dx of the bottom. Okay, let's put this in red. This is very, very wrong. Okay, please use the quotient rule. For the top part, it's f prime g minus g prime f over g squared. Okay, it's not so difficult to remember. So f prime g minus g prime f over g squared. You do not just differentiate the top and the bottom. Okay, that's wrong. Please, I don't want to see that again. Okay, so again, if you want to remember, f prime g minus g prime f over g squared. So the top part is very similar to the product rule, except you've got the minus there, and then you divide by g squared. Okay, so again, if you want to remember it, f prime g minus g prime f all over g squared. Okay, so that's the quotient rule. Okay, so once you use the quotient rule, you can substitute x equals 0. That was given in the point over there. And then we'll see f prime, sorry, rewrite that. So we'll see f prime at 0 is 1. Okay, so the gradient is 1. You could also write this as m equals 1. That's fine as well. And here the point said 0, 1. So we already know the y value is 1. So we can write this as y equals x plus 1. Okay, so you don't have to do any extra working. That was given from here. Okay, so that is the tangent line, or the linear approximation, or the linearized function. So if you're looking at this online, you might see different phrases for that. It all means the same thing. So if you're looking at other YouTube channels and so on, it will be tangent line, linear approximation, or linearized function. It all means the same thing. Okay, then we wanted to find the error. Okay, a few students did get this correct. One student got it almost correct. They just forgot the absolute value. Okay, the error is always positive. To make sure it's positive, we put absolute value and then the difference. Okay, please remember the absolute value part. And this was at a half, so we're going to have f at a half. So that is the actual function value minus the approximate value. We use our approximation there at a half. Okay, there's not much work, just put in your calculator, right? That will be 0.06 approximately. Right, 2 decimal places is enough for me to see if it's correct. If you want to put more decimal places, that's fine as well, but 2 places I can see what the answer is. Okay, but don't put 1 decimal place because maybe the answer will be 0 with the rounding. So please 2 or more, that should be fine. Okay, so if you want to write it as more, it will be 0.0556. That's fine as well. Okay, I can see quickly from rounding, I can see if you got it right or not. Okay, so again, the error, it's absolute value. Please remember that. I don't want to see negative errors. The function value at the point given minus the approximation value, again, at the point given. So in both cases, that's x equals 1/2. Okay, so problems I saw with this. A lot of students didn't know the error at all, so didn't know what to do. So they just substituted x equals 1/2 into the linear approximation. Please don't do that. The error is a difference between the actual function and the approximation. Okay, so issues I saw. Okay, so firstly, error is equal to f of x minus y. That's the formula. Please use that. Some students were saying that the error is just y. Okay, that's wrong. Others were writing error is equal to dy, and then they found the differential. That's wrong. And then others were writing the error is equal to df. Okay, again, that's wrong. Okay, so the error is always the difference between the actual value, the approximate value, and then we put absolute values just to make sure it's positive. Okay, so please do not. Okay, so that's right, that's wrong, that's wrong, that's wrong. Okay, so a very easy 1 mark question there. Just put in your calculator, you get your answer. Okay, question 4. Okay, so here we had the volume of a cone. So that was, 1/3 pi r squared h. Okay, we're given some dimensions for the cone. We want to define the rate of change of the height. Now, r and h, those are 2 variables. When we're taking the derivative, we want 1 variable. We need to eliminate one of them. Okay, we've done that again and again. So we need to write either r in terms of h or h in terms of r. Either way, we want 1 variable, not 2. How do we do that? Well, we can just put a little cross-section of the cone. I see a lot of students did this, which is good. The cone had a radius of 16. It had a height of 24, h and r. So we have the bigger cone or the bigger triangle. That's the cone when it's full, or just the cone itself. And then the smaller triangle, that's from the water inside. Okay, so 16 and 24, that's the full cone. R and H, that's the little cone inside with the water. Okay, now these are similar triangles, so we can write a ratio of R and H. So R over H, that's going to be 16 over 24. You can leave it like that, or you can simplify it to 2/3. So R equals 2/3 H. Or you can solve for H in terms of R and substitutes, right? The reason we solve for R and R in terms of H is because we want dH by dt at the end. So that's how we know what to get rid of. So we need to get rid of R. So here, V is equal to 1/3 pi. R we're going to replace with this now, H. Okay, so now V is going to be 4 pi over 9 times 3, 27, H cubed. Okay, that's a 3 there. Okay, so the squared from the R term and the H, that will make it H cubed. Now this H is not just a constant H, this is H of t. So when we differentiate, we need to use the chain rule. So dV by dt is going to be 4 pi over 27. Differentiating h cubed, that's going to be 3h squared. Chain rule, we differentiate the inside, that's going to be dH by dt, which is what we wanted. Now dV by dt, that was given as 8. So here we put in 8, h we put in 12, and then we can solve for dH by dt. Okay, so issues I saw with this, a lot of students were just ignoring R and just substituting some value for R, just ignoring it completely. Other issues I saw, dV by dt, students were writing this as d by dt, 1/3 pi r squared h. they were writing it as 1/3 pi times 2r dr by dth plus 1/3 pi r squared dh by dt. Right, doing like that. We don't know dr by dt, so that's not going to help us. So that's why on the first line we eliminated r by writing it in terms of h. It's because this bit we don't know, so this is not going to help us. So please, whenever you have some function of two variables, when we're taking the derivative, make sure you get rid of one of them so we're only working with one variable. In this case, we got rid of r and we left with h. So please do not do this because we don't know dr by dt. Okay. Other issues with this one, students were writing dv is equal to 1/3 pi r squared dh, right? As if we were doing that error approximation with the differentials. Okay, please don't do that. The error approximation with differentials is completely separate from rates of change. Okay, please do not do that. Okay. And then lastly, question 5. Okay, we had dv by dt was minus beta a. Okay, and it was also given v is 4/3 pi r cubed, and a was 4 pi r squared. What we wanted was dr by dt. Now, we have an equation, we have v, we have a, there's only one thing we could possibly do, and that's substitute. So, d by dt of v, we substitute. Minus beta a, we substitute. There's nothing else we can do except substitute what's given. Okay, let's take the derivative. So this will end up being 4 pi r squared, dr by dt using the chain rule. And then here, there's nothing else we can do, we just rewrite it. 4 pi r squared on both sides, we cancel, and we're done. Okay. There's nothing else you could possibly do with this question except look at the equation. We've got a v, we've got an a, we just substitute. So this was given, we substitute. This was given, we substitute. And then you just do the chain rule there. Okay. Quite a few students did get this right, so that's nice to see. A lot of students didn't try the question at all. Okay. Please write something down, right? Any attempt is good. If you just leave it blank, well, then you're guaranteed 0. If you try something, you've got hope for that. And then one more thing with this. With the derivative, a lot of students weren't using the chain rule. Okay, so we're looking for dr by dt. Please make sure that you use the chain rule. This r is not a constant, it's r of t. It's a function in a function, so we use the chain rule. Okay, so that's it for the test. Please make sure you go over this video again if you need to. It will be available on YouTube. If you have any questions to ask me, please ask. And you do have the tutors' contact information, so ask them as well. Okay, so on Thursday we won't have a proper tutorial session. As soon as the tutorial session starts, we'll start writing the test. Okay, so please don't be late for that. Okay, I'll see you then.